ايه هو هذا اللي حكاه. هاي راح اسجل المحاضره انا، راح اسجلها.
approach.
ماشي، واتركوها على اليوتيوب. على اليوتيوب يصير اسهل. حاضر. اذا مناسب بدك
Okay.
تاخذن خذن دنيا.
What is the dynamic programming approach?
عندي
The previous approach was divide and conquer.
عندي.
In short, we can say DC. DC stands
هاي
for
المحاضره
divide
شنو؟
and
لا لا
conquer.
لا لا سيد.
In divide and conquer approach, we have three steps: dividing steps, recursively solving the subproblems, and then combining steps. Um, we can say DP for short to dynamic programming approach. DP is similar to DC, but also differs in some aspect.
يلا ان شاء الله باذن الله. يلا بالسلام. الله معك. هلا.
In fact, the dynamic programming approach is an improvement of DC. DP, we can say DP is an improvement on DC. How DP improves DC? In DP, we consider a data structure in memory for saving the solutions of the subproblems. So we have a data structure in memory, and we save the solution of sub problems in it. So if we have duplicate subproblems, I mean subproblems that are the same, subproblems that are similar each other, we can we can solve one subproblem and save its solution, and for the other subproblem that is similar to the previous one, we do not solve it again, and we use the previous solution because we have already the solution in the memory. So if we have duplicate subproblems, we solve only one subproblem, and for this other subproblems, we use the previous solution which has been stored in the data structure in memory.
والله الحمد لله.
This improves the method, and we have less time complexity. We can save the time, and we do not need to solve similar subproblems again and again. We only solve one subproblem, and the similar subproblems use the solutions that are stored in the memory. Let me describe this method during an example. Suppose we are going to multiply some matrix matrix M1 is multiplied by M2 is multiplied by M3 and so on until matrix Mn. So the example or the problem that we consider here is matrix multiplication. Matrix multiplication. We are going to multiply some matrices. When we are going to compute this multiplication, we can do parentheses. We can do and we can have parentheses on this multiplication. I mean, if we are going to multiply for matrix, for example, for matrix, there are various parentheses for this multiplication. We can multiply first M1 by M2, then M3 by M4, and then the result of the first multiplication is multiplied by the result of the second multiplication. Also, there are some other possible parentheses. For example, we can first multiply M1 by M3, then the result is multiplied by M4, then M1 is multiplied by the previous result. Also, we may do like this. M1 is multiplied by M2, then M3, then M4, and so on. So there are various parentheses we can do. We can put parentheses in various ways for multiplication of matrices. And this parentheses has effect on the number of multiplication. What I mean is I am going to explain what do I mean. Suppose M1 is going to multiply by M2, M3, and M4. Every these matrices are two-dimensional. For example, suppose matrix M1 have 5 rows and 100 columns. Matrix M2 has 100 rows and 10 columns. M3 10 rows and 50 columns, and matrix M4 has 50 rows and 25 columns.
سلام الله وبركاته. خلص شلون صحة؟ خلي ان شاء الله يبارك فيك.
If a
هوية
matrix is multiplied by the other matrix.
سريع سريع تفضل.
The result is another matrix. Suppose
على
the
الراس.
first
لا
matrix
بالعكس،
is
صوتنا
matrix
على راسي.
A, which has P row and Q column. What the second matrix is matrix B, which has Q row and R columns. The result will be a matrix C, which has P rows and R columns. When we multiply a matrix by dimension PQ to a matrix by dimension QR, the middle dimension is removed and the result has the dimension of the first dimension, and the number of columns is the last dimension, I mean R. So if we multiply A, which is which has PQ dimension, by matrix B, which has Q and R dimension, the result is a matrix C, which has P and R dimension. Okay. Uh, how matrix C is computed is like this. Matrix C has some items in each row and columns. The number of rows is P, the number of columns is R. Each item of matrix C is computed by multiplication of one row of matrix A in one column of matrix B. Then the number of columns of matrix A is Q. The number of rows of matrix B is also Q. Each element of a row, each element in every row of matrix A is multiplied by an element in a column in matrix B. So the number of multiplication for computation one item of matrix C is Q. Let me have a real example. Suppose we have this matrix 2, 3, 4, 1, 2, 3. For computing the result of this multiplication, we multiply the first row of A to the first column of B one by one. I mean 2 is multiplied by 5, then it is plus by multiplication of 3 to 1 plus multiplication of 4 by 2. The result is 21. So we have 21 here. Then the first row of A is multiplied by the second column of B 2 is multiplied by 3 plus 3 is multiplied by 2 plus 4 is multiplied by 2. The result is 20. Here is 20. Okay. Then the second row of A is multiplied by the first column and then second column of B. 1 is multiplied by 5 plus 2 is multiplied by 1 plus 3 is multiplied by 2. We have 13 here. And the second row of A is multiplied by the second column of B. 1 is multiplied by 3 plus 2 is multiplied by 2 plus 3 is multiplied by 2. This is 13 again. Okay. So for computing one item of matrix C, one row is multiplied by one column. One row of A is multiplied by one column of B, and the number of multiplication is Q. If we have Q column in A and Q rows in B, the number of multiplication is Q. If A is P multiplied by Q, has P and Q dimension. The number of row is P and the number of column Q. B, the number of row is P and the number of columns is R. C will be P multiplied by R. Has P rows and R columns. And for each item of C, we should do Q multiplication. So the total multiplication for computing C is P multiplied by R multiplied by Q. This is the total multiplication for computing C. Total multiplication for computing matrix C. Okay. So we should do P multiplied by R multiplied by Q multiplications for computing matrix C for multiplying A to B. Okay. Now let's consider the previous example. I mean this for matrices. We can do this multiplication by various parentheses. If we consider two different parentheses and compute the number of multiplication that are down, we notice that the number of multiplications is affected by the parentheses. Consider two different parentheses uh, for that four matrices. If we do in this way, and if we do in another way, we're going to compute the number of multiplications in these two different parentheses. In the left side, m1 is multiplied by m2. m1 is the dimension of m1 is 5 rows and 100 columns. Dimension of m2 is 100 rows and 10 columns. So if we multiply m1 and m2, we will have a matrix whose dimension is 5 and 10. I mean 5, the multiplication of m1 and m2 has 5 rows and 10 columns. How many multiplications is done when we multiply m1 by m2? As we said in the previous slide, PRQ multiplications is done. So 5 multiplied by 10 by 100 multiplied by 10, which is 5,000 multiplications. Okay. Number of multiplication will be 5 is multiplied by 100 is multiplied by 10, which is equal to 5,000. 5,000 multiplications is done when we multiply m1 by m2. The result is a matrix which has 5 rows and 10 columns. Then we multiply m3 and m4. m3 has 10 rows and 20 columns. m4 has 20 rows and has 50 rows and 25 columns. When we multiply these two matrices, the result is a 10 multiplied by 25 matrix. And how many multiplication is done? Number of multiplications, number of multiplications will be PQR. 10 multiplied by 50 multiplied by 25. 10 is multiplied by 50 is multiplied by 25, which is which is 12,500. Okay. Okay. And then a 5 multiplied by 10 matrix is multiplied by a matrix that has dimension 10 and 25. The result will be a matrix with dimension 5 and 25, and the number of multiplications in this step will be, because we are going to multiply these two, we have 5 multiplied by 10 multiplied by 20 multiplication. 5 is multiplied by 10 is multiplied by 20, and the number of multiplications here will be 1250. Okay, the total number of multiplications will be, we have 5,000 here, 12,500 here, 1,250 here. The total will be 18,750. Okay. What about the right side? I write it in the next slide. We are going to multiply M2 by M3 at first, then multiply to M4, and then we multiply M1 by the results of the others. So at first we multiply M2, M3. M2 has 100 rows and 10 columns. M3 has 10 rows and 50 columns. If we multiply these two, we have a matrix of 100 rows and 50 columns. The number of multiplication is what? It is 100 is multiplied by 10 is multiplied by 20. 100 multiplied by 10 multiplied by 20, which is 50 thousands. 50 thousands, not 5,000. Then M4 is multiplied by the result. M4 is has 25 rows and has 50 rows and 25 columns. If it is multiplied by the previous result, we have 100. We have a matrix with 100 rows and 25 columns, and number of multiplication will be we have here 25 rows, we have 50 rows and 25 columns, which is multiplied by a matrix that has 100 rows and 50 columns. The number of multiplications is 100 is multiplied by 50 is multiplied by 25. 100 is multiplied by 50 is multiplied by 25. It's 125 thousandths. And in the last step, M1 is multiplied by the result. M1 has 5 rows and 100 columns. Result has 5 rows and 25 columns, and the number of multiplication which is done in this step is 5 is multiplied by 10 by 100 is multiplied by 25. So total number of multiplications will be uh, we have 50,000 here, we have 125,000 here, and 12,500 here. Will be this. Uh, 187,500. Okay. 18,750, but here it is 10 times bigger than the previous one. Okay. This example shows that the manner in which we do parentheses in multiplication of matrices will affect the number of multiplications that are done. Okay, so it is important. It is important that how we do parentheses. Any question? Okay, so parentheses is important in in matrix multiplication. So we should find the optimum parentheses. What's the optimum parentheses? We should find a parentheses that that in which the number of multiplications is minimum. Okay, we are going to find the parentheses that gives us the minimum number of multiplications. Finding optimal parentheses Okay. Yes, please. By optimal parentheses, we mean the parentheses that give us the minimum number of multiplication. Uh, okay, let me explain again. When we are going to multiply some matrices, we have various options for doing parentheses. For example, for these four matrices M1, M2, M3, and M4, various parentheses are possible. In the left side, we multiply M1 by M2, then M3 by M4, and the results are multiplied by each other. In the right side, at first we multiply M2 and M3, then it is multiplied by M4, and the result is multiplied by M1. We are going to compute how many multiplications are done in these two different parentheses. In the left side, we compute the number of multiplications. At first, we multiply M1 and M2. In multiplication of M1 and M2, the number of multiplications that are done is 5 multiplied by 100, 100 and multiplied by 10. So the number of multiplications is 5,000. In multiplication M3 and M4, the number of multiplications is 10 multiplied by 50 multiplied by 25. So the number of multiplications is 12,500. Then the results of the M1, M2 is multiplied by the result of M3, M4. The result of multiplication of M1 and M2 is a matrix with 5 rows and 10 columns. The results of multiplication of M3 and M4 is a matrix that has 10 rows and 25 columns. If we multiply the left side and the right side, we give a matrix that have 5 rows and 25 columns. The number of multiplications here is 5 multiplied by 10 multiplied by 25. So the number of multiplications here is 1,2500. If we sum up these three, we get 18,750. This is the total number of multiplications that are done in this parentheses. Now, let us consider the right side and other parentheses. We consider it in the next slide. Okay, here first we multiply M2 and M3. The number of multiplication that are done in this multiplication is 100 multiplied by 10 multiplied by 50. So the number of multiplications are the number of multiplications is 5,000. Excuse me, 50,000. And we get and the result is a matrix that has 100 rows and 50 columns. Then it is multiplied by M4. M4 has 50 rows and 25 columns. So the number of multiplications that is done here is 100 multiplied by 50 multiplied by 25, which is 125,000. This is the number of multiplications, and the resulting matrix has 100 rows and 25 columns. Then we multiply M1 to this one. M1 has 5 rows and 100 columns. The number of multiplication will be 5 multiplied by 100 multiplied by 25. And the number of multiplications here will be 12,500. So the total number of multiplications is summing up these three. So we have 187,000 and 500 multiplications. This is 10 times bigger than the previous one. The previous one was 80,000, 18,000. The second one is 180. Okay, so it is 10 times bigger than the previous one. This example shows us that the parentheses and how we do parentheses can affect the number of multiplications. So parentheses is important. Different parentheses results in different number of multiplications. So when we are going to multiply some matrices, we should do this multiplication in an optimal manner. We should find the optimal parentheses for multiplication of matrix. By optimal parentheses, we mean the parentheses that gives us the minimum number of multiplications. We are going to find this optimal parentheses. Okay? Any question? Okay. No. We should. Allah Shalif is asking a question. Your question is about what slide? Slide 8. Do you ask me to explain slide 8 or slide 7?
Assalamu alaikum, Doctor.
Assalamu alaikum.
I'm sorry, Doctor. I mean, this slide, yes. Why M1 is value 5 multiply 100? Why use 100? Yani? And I mean 5 multiply 10, okay? And this right and left multiply 10, okay? Number. And we divided M1, M2, M3, M4, okay? but why we use 100 multiply? 5 multiply 100 for M1. M2 100 multiply 10. Answer. Why we use 100?
And these are the dimensions of the given matrices. Consider this matrix we have. We are given these matrices. Matrix M1 has 5 rows and 100 columns. Okay. Matrix M2,
That's clear.
okay, has 100 rows and 10 columns. This is the input. These matrices are given to us. The dimensions are these. M3 has 10 rows and 50 columns. M4 has 50 rows and 25 columns. We are going to multiply these. And in this slide, if we multiply a matrix which has a matrix A, which has P rows and Q columns, if this matrix is multiplied by matrix B, which has Q rows and R column, the result will be a matrix C, which has P rows and R columns. The middle dimension, which is Q, is omitted in the result. We do not have Q here, just the first one and the last one, P and R. Okay, but when we multiply these two, for each element of C, we do Q multiplication. This one row of A is multiplied by one column of B. One row of A has Q elements, one column of B has Q elements. These two are multiplied, and the number of multiplications for any element of C is Q. In C, we have P multiplied by R elements, and for each of them, Q multiplications are done. So the total number of multiplications for computing C is P multiplied by R multiplied by Q, as we said in the next slide. Okay, then in our example, we consider two different multiplication. The multiplication in the left side and the multiplication in the right side. In the left side, M1 is multiplied by M2, then M3 is multiplied by M4, and at last, the results of the left side is multiplied by the result of the right side. Here, M1 has 5 rows and 100 columns. M2 has 100 rows and 10 columns. These two matrices, when is multiplied to each other, the result is a matrix that has M rows and 10 columns. 100 is omitted here in the result, but the number of multiplication that are done in multiplication of M1 and M2 is 5 multiplied by 100 multiplied by 10. This is the number of multiplications. Also for M3 and M4, if we multiply M3 that has 10 rows and 50 columns to M4, which has 50 rows and 25 columns, we get a matrix that has 10 rows and 25 columns, and the number of multiplications is 10 multiplied by 50 multiplied by 25. At last, the left side is multiplied by the right side. In the left side, we have a matrix that has 5 rows, 10 columns. In the right side, 10 rows and 25 columns. These two are multiplied to each other. The number of multiplications is 5 multiplied by 10 multiplied by 25, as we wrote here. And the result is a matrix that has 5 rows and 25 columns, as we write it here. Then we sum the number of multiplications and we get this one. In the next slide, we consider the other parentheses. For the other parentheses, also we compute the number of multiplications, and we get this one. Is it clear? Yasir Jassim asks another question. Yes, we can try other parentheses. There are many parentheses. We can consider other parentheses. The question here is, what parenthesis is better? What's the optimal parenthesis? We are going to find the optimal one. Okay. There are many parentheses. Which one is the best? We are going to find that. We are going to find the optimal parenthesis. Another a student asks what we use parentheses. We must use parentheses. We do not have any other options. When you are going to multiply some matrices, you do this multiplication in some order. You should use some order for doing multiplication. This order defines the parentheses. Okay, if you first multiply M2 by M3, so you have a parenthesis for these two. Then we are going to do the next multiplication. Which is the next multiplication? If it is the multiplication between M2 and M3 and M4, so the parenthesis is like this. So the order in which we do multiplication defines parentheses. We have to use parentheses. We do not have other option. But the question here is which parenthesis is better? When you are going to multiply matrices, you should start from one of the multiplication operation, then the second multiplication, then. So you have an order for multiplication. This order is your parenthesis. This order defines a parenthesis. Okay, we have to use parentheses. Do not have any other option. But question here is, what parenthesis is better? What order of multiplication? How we multiply? What order is better? As you see in the previous slides, in slide 8 and slide 7. If we first multiply M1 by M2, then we multiply M3 by M4, and then we multiply the results of M1, M2 by the result of M3, M4, we get the left side parentheses. In the right side, if we start multiplying M2 and M3, then we multiply the result by M4, then we multiply M1 to the last result, we get the right side parentheses. The question is, which one is better? From these two, the left side is better. But for all parentheses, for all possible parentheses, what is the best? We are going to find the best. Okay. As I told before, in any parentheses, one of the multiplication operation is the last. For example, in the left side, the last parenthesis in the left side parenthesis is this one. This multiplication is the last multiplication here because the last operation that is done is this. In the right side, first you do this multiplication. The second one is this one. Left side, the result of the left side is multiplied by the result of the right side during doing the last operation. In doing the last operation, some multiplications are done. The number of multiplication in the last operation is what we wrote here. The number of multiplication in the last operation is are the multiplications that are done during the last operation. C1k is the number of multiplications in the subproblem 1 or in left side. Ck plus 1 and n is the number of multiplications in the right side. And C1n is the total number of multiplications in multiplying M1 to Mn matrices, the total matrices.
Excuse me, doctor.
Yes.
Do you meant by optimal it's the final or the last multiplication? So is that meaning the last operation? It's mean the optimal?
No, by optimal parentheses I mean the parentheses that give us the minimum number of multiplication. For example, here in the left side we have a parenthesis, okay. In the right side we have another parenthesis. By optimal I mean which of these parentheses is better. We are going to find the best parenthesis. The best parenthesis is optimal. We are going to find the best parenthesis. And in that parenthesis, we get the minimum number of multiplication, the minimum number of possible, the minimum number of possible multiplications. So the number of multiplications in the best parenthesis is minimum, is optimal. So we are going to find a parenthesis that gives us the minimum number of multiplications. If we are doing the multiplication in a way that parenthesis according to that parenthesis, we get the minimum number of multiplications. So if we do parentheses in any parentheses, one of the operation is the last operation. So we are going to find the last operation in the optimal parentheses. We are going to find in the optimal parentheses which operation is the last operation. Okay. In this parentheses, the last operation is this one. In the left side, last operation is this one. In the optimal parentheses, there is a last operation. We are going to find that operation, and using that we can find the best parentheses. If we suppose that this is the best parenthesis, this is the optimal parenthesis, and in this parenthesis the last operation is here. Yes, you suppose that the last operation is here between k and k plus 1. If this is the last operation, then we can divide the problem from this point, and we can write a relation between the number of multiplications of the left side, right side, and total number of multiplication. The total multiplications that are done in these parentheses are the multiplications that are done in the left side plus the number of multiplications that are done in the right side plus the multiplications that are done during the last operation. Okay, the total number of multiplications that we have are the multiplications that are done during the left side plus the number of multiplications that are done during the right side plus the multiplications that are done during the last operation. This is the total number of multiplication. So we can write this relation. The total number of multiplications is equal to the number of multiplications of the left side plus the number of multiplications of the right side plus the number of multiplications in the last operation. This is for sub problem 1. This is for sub problem 2.
Doctor, in the previous exam, we took to the left side alone, and then we returned to the right side and solve it each one it's separately. So could we get the full equation for this one, for this example, so we can know what we did here? We understand the example, but we understand each one separately, the left side and the right side. So it's already distributed to two parts, left and right. So could we get the full equation so we can know how we divide it into two sides, please, if possible?
Yes, I am going to explain. I should explain more. Okay. There are something that I should say. The following. Okay. Suppose we have a matrix Mi, okay, and its dimension is di minus 1 and di. Di minus 1 is the number of rows of matrix Mi, and di is the number of columns of matrix Mi. Then mi is multiplied by mi plus 1, and so on, multiplied by mk. The dimension of mk is dk minus 1 multiplied by dk. For mk, the number of rows is denoted by dk minus 1, and the number of columns by dk. Then it is multiplied by mk plus 1. The dimension of mk is dk for the number of rows, and dk plus 1 for the number of columns. And at last, we consider we have mj, the last matrix, with dimension mj minus 1 and dj minus 1 and dj. Suppose we are going to multiply these matrix from mi to mj. Okay, we denote this problem by pij. Pij is a problem in which we are going to multiply matrix mi to matrix mj. Okay, we are going to find the optimal parentheses here. We do not know before which parenthesis is the optimal, and we do not know which operation is the last operation. Okay, we do not know which of these multiplication operation is the last operation. We do not know the optimal order of multiplication. But but suppose that this multiplication is the last one. If this is the last operation, suppose this is the last operation in the optimal parentheses. We do not know which one is the last, but assume that this is the last one. If this is the last one, then in the optimal parentheses, the left side is computed. The left side parenthesis is computed separately. The right side parenthesis is computed separately. And the result of the left side is multiplied by the result of the right side. Okay. The result of the left side, if we show it by m prime, suppose m prime is a matrix that is the result of the left side. This matrix has what dimension? As I said before, when we are multiplying some matrices, the middle dimensions are omitted, and at last the first dimension and the last dimension remains. So the result of the left side has dimension di minus 1 and dk. So m prime is a matrix with dimension di minus 1 and dk. Okay, I mean, if we multiply mi to mk, if we multiply these matrices each other, the final result of the left side is a matrix that has di-Hayek rows and dk columns. So we have a matrix M prime in the left side as the result of the left side, which has di-Hayek rows and dk columns. For the right side, suppose the result be matrix M Zegon. This matrix has dimension dk and dimension dj. dk dj, because when we multiply, oh sorry, Google Meet is disconnected. Uh,
منو هذا منو هذا؟
in Google Meet. Okay. Uh, do you hear me on Google Meet?
Yes, Doctor. Thank you so much.
Okay. Let's continue. Okay. So if we multiply the left side, if we multiply the matrices on the left side to each other, the result is a matrix. The final result of the right side is a matrix that has dk rows and dj columns, because the middle dimensions are omitted, one by one are omitted, and the only first dimension and the last dimension remain. So the result is a matrix with dk rows and dj columns. So when we are doing the last operation, matrix M prime is multiplied by matrix M zegon, and because dimension of M prime is Diemann Hayek dk, and the dimensions of M zegon is are dk dj, the number of multiplications in the last operation will be Diemann Hayek multiplied by dk multiplied by dj. So we can write this: the number of multiplication, the number of multiplications in the last operation is equal to d I minus 1 multiplied by dk multiplied by dj. In the previous slide, we have here the number of multiplication in the last operation. So this term is equal to d I minus 1 multiplied by dk multiplied by dj. So we can rewrite the formula in problem Pij. We are going to multiply mi to mj. We can denote the number of multiplication by Cij. Cij, let Cij denotes the total number of multiplication in problem Pij. Okay. In the left side we have Cik. In the right side we have Ck plus 1j. So we can write this: Cij, which is the total number of multiplications, is equal to the number of multiplications that are done in the left side, which is denoted by Cik, plus the number of multiplications on the right side, which is denoted by Ck plus 1j, plus the total number, plus the number of multiplications that are done during the last operation, which was di minus 1 multiplied by dk multiplied by dj, as I wrote in the previous slide. So we get this formula. In this formula, we assume that the last operation is between mk and mk به اضافه 1. In this formula, we assume the last operation is between mk and mk plus 1. Okay, as we said in the previous slide, we assume that the last operation is here, but we do not know where is the last operation. Okay, so what we do? So what we can do is to consider all the options. The last operation may be between mk plus 1, or maybe between mi plus 1, or any of these operations. So we can consider all the possibilities, and between these possibilities select the best one. So we can rewrite the formula as this: mij is equal to mean for any k between I and j, c I k plus c k plus 1 j plus d I minus 1 multiplied by dk multiplied by dj. There are some possibility for the last operation. The last operation may be between mi plus 1, between mi plus 1 and mi plus 2, between mk plus 1 to between mj minus 1 and mj. So the last operation has some possible options. We consider all of the options, and between them select the minimum one, select the best one. So k can vary between I and j minus 1. So here we let k vary between I and j minus 1. We write here k greater than or equal to I and less than j. Between all possibilities, we select the minimum one. Okay, this is the final formula. Any question?
Thank you so much, Doctor.
This means that the last operation may be any of the multiplication operation. Any of the multiplication operations can be the last